Okay, hello everybody. I'm going to give you a demo of a tool called Formula. This tool helps you to construct good software architectures. So maybe if we just turn to the slide really quickly, I'll give a little introduction. The idea here is that if you want to design a software architecture from a bunch of components, where a component may do something like encapsulate a web service, then you may know on the surface of this component a lot of information about what the web service inside would do. So for example, you may know that it produces integers, which is kind of the usual thing you would know, but you can know more about it. Maybe that it produces these integers at 5 times a second. So this is a more interesting property of the component. The problem then is to wire these components together so that the system makes sense. So one way that it might not make sense would be if this component requires data at a rate which is higher than the component here produces data. So if you would wire such a system together, then without even implementing it, you may know that it's a bad architecture. So that's beneficial if you have the information about these components to be able to know early that the software architecture is a bad one or a good one. Now, to be more realistic, you often have to consider the actual hardware on which the software will run to really know if the architecture is good or bad. So this is the so-called deployment problem. And here it requires also a model of the hardware platform on which the software will run. And what you have to do in addition to building the software architecture is to place the components onto the nodes in some way. What existing tools can do is to tell you when you've made a mistake. So they might be able to tell you, well, if you try to run both of these components on the same node, that because they share the same node, they'll run too slowly to produce the data that the component over here needs. So it's good that you can get these mistakes early before you actually implement. On the other hand, you have to somehow correct a problem. And this is where it gets hard, because if the constraints on how you construct the architecture are good constraints, then they're also probably difficult to solve. And that's what the research that we have been doing with Formula attempts to address. It will try to solve the architectural problem for you once you've explained the constraints that you have to follow, the rules of the game. So I'll give you a demo now to show this in more detail. Okay, so let's start out with a simple example. So what you see here is our specification language called Formula. And what I'm going to do first is to specify a very simple abstraction for the software architecture. This will give us the notion of components and connections. So I write this little keyword domain and software. This declares that I'm going to define a new abstraction. In this abstraction, I will add some key concepts that we need to talk about architectures. So the first thing I add is the idea of a component. A component is just something which I can create by giving it an ID and a frequency which describes how often it will produce data. I'll also add the notion of a connector. A connector is something which takes one component and connects another. And this gives us the ability to say that data flows between components. So that's a very simple idea of an abstraction. I'll leave out the rest of these details for maybe later questions. But once we write this down, we now have the ability to build a model of a system by instantiating a bunch of components and connectors. Okay, so that's a simple example of what abstraction would look like. Let's look at another one. So in the same file, but under a different domain, I'll now define what lives in the platform. So again, this will be a bit simple. A platform will have a node, the concept of a node, which will have an ID, the concept of a function, which is something that can run on a node. And to make it a little more interesting, you can see in the language that we can kind of play with these abstractions. So I can take the platform abstraction and I can extend it with the notion of worst case execution time, where this will say, if I run a function on some node, this is an upper bound on the amount of time it takes to actually run that function on that node. Okay, so still pretty simple here. Now I'm going to make it a little more complicated. So in this example, the hard part will be the deployment problem, how to place these components onto nodes. So the first thing we have to do is to take these two abstractions of software and platform and combine them to be able to talk about this deployment problem. In our language, this composition is enabled by this little star here. So the star allows us to take the specifications and combine them. And then we can add to this the notion of a map, where a map says you can place some module from the software onto some node in the hardware. In addition to this map, we include here a bunch of constraints. These are called schedulability constraints, and if you can satisfy them, it means that the system that you build will always be able to produce data quickly enough to be consumed by other components in the system. It's also well known that these schedulability constraints are computationally difficult to solve. So if you would have a big system, you will not be able to, on the back of the envelope, sort of figure out how to solve these constraints for a large system. And that's what Formula can do for you. So to show how this works, I'll take this mapping domain, this mapping abstraction, and build what we call a partial model. This is a model of a system where there are some unknowns. So the things I do know are there are some components, some nodes where I can run things, some functions. So essentially a bunch of the aspects of the architecture I know. In this example, what I don't know is how to map a module which clusters some components onto some node. So these underscores represent the unknowns in this model. And in order to fill them in, I have to reason about all of those constraints that I just showed you. And that's what the tool can do for you. So I'm just going to go over here to the right and click on this partial model and ask it to try to find a solution that fills in these unknowns. It thinks for a moment, and this is what we get back. We get back a model where the partial has been removed. There's no more partial keyword. That means that there's no degrees of freedom. There are no unknowns left. So this contains everything we put in the beginning, components, connectors. And if we look at the map, we see that the map has now been fully instantiated. So the underscores have been replaced with nodes, where this explains if you put this module onto this node, if you put this module onto that node, then you have a complete system which will satisfy all of those constraints. We can just overlay a visualization of this to make it a little bit easier to understand. So the visualization that you see here shows the nodes which can run the software components, their interconnections, as well as the modules which cluster some components together. And it also shows what the tool computed. Was this arrow here, which says how you place a module clustering components onto some nodes. So if you run all of these here, you run all of these here, you follow those rules, then you get a system which is schedulable. And that in this case is the hard part to solve. The tool can also do more than just show you one architecture that satisfies all of these rules. It can try to find many architectures to show you the different ways that you could build a system. So I can go back over here and ask for 10 more models. It will now think a little bit longer and pop out other ways that we can build a system. So I can just, let's just grab one of these and look at them. So you can just sort of tell by switching between the two diagrams that the placement of the modules are quite a bit different from these two solutions. And that's not by coincidence. So the tool is actively trying to find different solutions to the same problem to give you a sense of the different ways you can solve the problem. So this is, one term for this is design space exploration. The tool helps you explore the possible space of designs while satisfying this sort of complex set of constraints that distinguish meaningful designs. So that's the idea of Formula. That's the basic demo.
Okay. So this is from released yet?
So Formula is not released yet. We hope to have it available for download in a month or so. So there's still some work to do before it will be available, but we'll have it on the Microsoft Research RiSE site, Research and Software Engineering, which is actually on this poster right here. Maybe you want to just catch it. So if you go to research.microsoft.com/RiSE, you have a website which has the projects from our group, many other cool projects to download as well, and we'll have a link to Formula from this website.
Okay.
Yeah.
So Ethan, do you work as a Microsoft researcher?
Yeah. Yes, that's right. So I'm a researcher at Microsoft. I joined about 3 years ago. I did my PhD thesis on model-based development of embedded systems, is initially where I come from. And since I joined Microsoft Research, that's continued to be my research focus. Tools to help you design complex software systems using modeling techniques. And that's what we tried to provide with Formula, state-of-the-art tools to help you do modeling. Yeah.
Thank you so much.
Okay. Thank you.
See you later.
Okay, bye.